So this video and the next few videos will be about what's called multi-class logistic regression, and we will discuss two approaches. Okay. Um, so far, we focused on binary classification using logistic regression, right? That is, we were able to classify data that belong to one of two categories. For instance, we looked at 5 versus not 5. In your homework, you did even versus odd. We looked at sort of simplified cases of material failure versus not material failure. In any case, we were able to use logistic regression to divide data or divide the space of possible data into two classes, and we were able to divide the space using linear or planar separating boundaries, or sometimes quadratic or cubic or other more complex separating boundaries. Okay, so we use logistic regression for that. Again, binary classification. But really, in general, we would like to do multi-class classification, or essentially distinguishing some data point from among m different classes, okay, or n different classes. How do you do that? Approach number one, which is perhaps the simplest thing that one might think of, is using m binary classifiers or n binary classifiers, as many classes as there are, as many classifications as there are classes. Okay, so how do we do that? So let's say we have more than two categories. Let's say we have 10 categories, and let's say they're labeled, for instance, 0, 1, 2 until 9. Really, these could be anything. It so happens that in the MNIST character data set, these literally are the numbers in the images. But you can imagine images with 10 different types of objects, or sounds with 10 different kinds of words, whatever, doesn't matter. So how do you, given a new data point, how do you classify that new data point? Okay, so two steps. First is actually to train a classifier, and the second step is to use the classifier. Step one, given that we know how to solve the binary classification problem, we just solve, in this case, 10 different logistic regression problems, each of which is a binary classification problem. Okay. Specifically, in this particular case, we would first build a binary classifier between 0 and not 0, and then a binary classification between 1 and not 1, 2 and not 2, etc. Right? 3 and not 3. So 10 different, or as many classifiers as there are data classes. Okay, so first get those, how many of our classifiers. Then once we have those things, we can use them. Okay, so say we have, for each of these classifiers, we use sort of linear decision boundary models. In other words, z equals b naught plus b1 u1 plus b2 u2, etc., where uy are the different input variables. And really, this could be any expression. I just for illustration purposes, I picked the linear version, but you could have quadratic, cubic, doesn't matter. Okay, but effectively, we have these unknown coefficients. And once you actually do the logistic regression, these coefficients will be known. And you'll have these coefficients for each class. Okay. Because these coefficients list is known for each class, I'm going to put a subscript, but a different kind of subscript. Instead of just saying b equals this thing, I'm going to say for class 0, we have these coefficients b 0. For class 1, we have these coefficients b subscript 1, and so on. Subscript I put within brackets just to distinguish between these kinds of subscripts, right? For MNIST, because it's got 784 pixels, or basically 784 inputs, your B vector will have 785 coefficients, but you'll have 785 coefficients for each of the 10 different classes. Okay, so you really have 10 times 785 coefficients, or 7,850 coefficients now. Once you have solved the logistic regression problem 10 times. Okay. Okay, so you've got these 7,850 coefficients, or 10 times 785 coefficients. What do you do with them? So what you do with them is, now if you're given a new image, you can use these coefficients to say, is this image that has a 0 or a 1 or a 2, whatever, or which object the image contains. How do you do that? So the image itself, if it's MNIST, let's say, is 784 dimensional. Like you said, it could be any data set. I'm just using MNIST as an example, high dimensional data set. So each pixel value is going to be like U1, U2, U3 to U784. So it's a point in 784 dimensional space, right? Okay, so you take this and then essentially compute the z value, but then you compute the z value with this b, this b, this b, and so on, right? So you compute 10 different z values, one for each class, for each image. So given an image, you use the coefficient vector for class 0, you compute a z value, and then use the coefficient vector for class 1, compute the z value, and so on. Basically, you're computing this expression for each set of coefficients, but for the same image. Okay, so now you have, for a given image, 10 different z values. Previously, we used to just have one z value, and we classified the image into a 0 or a 1, basically, whether it belonged to the 0 class or the 1 class, based on whether z was greater than 0 or less than 0. But now we have 10 different z values, and again, one for each class. So which class does it belong to? The procedure is pretty simple. You just pick the class that has the highest z value. Okay, so among the 10 different z values, you pick the class that has the highest z value. In some very crude sense, the highest probability of among all the different classes. And then if you want to assign a second best class or second best guess for what the class is for a particular image, you can pick the next highest z value and so on. Okay. So that's the method, pretty simple. It's a very simple step beyond what we did. You do 10 different or how many ever different logistic regressions, and then compute the z value for each of those classifiers given a new data point, and then use those 10 or m different z values to guess or predict or decide what the best category you should put this new data point into. Okay, this method, we will see a demonstration of this method in a minute on MATLAB. You'll find that it's pretty good for the MNIST database. Not amazing, but pretty good. Certainly much better than chance. We'll see how good it is, I guess. The downside of this methods are the following, and they will be sort of fixed in approach number 2. The first downside is that if you view, so recall when you have two classes only, your logistic function operated upon zi was basically a probability that the data point belonged to that class. But when you have 10 different classes and 10 different zi's, it turns out you can do logistic of z of I, but unfortunately, and you will get a number between 0 and 1, which superficially, well, for that particular regression is the probability that it belongs to class I versus not class I. But then if you add together all the probabilities, like all the basically logistic function applied on the zi, those probabilities will not add up to 1, because these probabilities have been computed independently of each other. There is no reason really, unless the data was contrived in some manner, that these probabilities should add up to 1. So it is a bit unsatisfactory. Like the classical logistic regression with binary classification had this nice feature that the logistic function operating on the zi is actually an estimate of the probability that it belongs to a particular class. If we do these n different binary classification problems, you sort of lose that interpretation, unfortunately. The second downside is that we are doing n different binary classification problems in a sort of decoupled manner, like in a sort of independent manner. When we are trying to find the classifier for 0, we are not really using the fact that the rest of the data is actually not one big class, but divided into, well, 9 different classes, for instance. So we are sort of throwing away information while doing these n different independent binary classification problems. And it turns out that you can do better. You can use all the data available in a more holistic manner rather than treating them independently. And the next approach, as I say here, does this thing. So there are some downsides. Nevertheless, this is a really simple extension of the binary classification logistic regression. And we will see a MATLAB implementation of this in a second.